All right, here we are with day 5 of Advent of Code from 2022. Uh, this was actually slightly more challenging problem than the previous days. We can see right away that our input to this puzzle is a bit more complicated because we have to essentially parse this stack of crates. What is happening in this puzzle is that we've got a stack of crates, and we've got a series of instructions for how a crane will move these crates back and forth between these stacks. So, for instance, we can see, okay, so we move one crate from column 2 to column 1. And so what happens, as we see in the next picture, is that this D crate gets moved from column 2 to column 1. But we can also move multiple crates. So when we move 3 from column 1 to column 3, what happens is that the D crate gets moved first, the N crate gets moved second, and the Z crate is moved third. So this is sort of the result of that. So what we're really doing here is we're keeping track of this stack of crates, and we are running through all of these different moves. And at the end of the day, what we have to do is spell out the letters that are on top of each of the stacks. So algorithmically, it's not that complicated because really it's just a pretty simple state evolution problem. But the parsing step is definitely a little trickier than what we've seen so far. And in fact, let's see, how many lines of parsing code did I write? All the way down to 94. So yeah, I wrote like, between the type definitions and the parsing code, it's almost like 60 lines of code. So a fair amount of stuff there. So the easiest thing to start with is just the actual moves themselves. So this part down at the bottom, this is pretty straightforward. We have just a number of different lines, and we have all these keywords in here. So that's really simple to write. We have move, we parse a number for the number of crates, and just other strings, other numbers. And we have this data type representing a move. So it's a number of crates, the source column, and the destination column. That part's pretty easy. So to get all of these together, again, I forget where, but yeah, here we just say sep n by 1, parse move, end of line. That part's actually fairly easy. Parsing the stack of crates itself, that's the first step, and that's a little more challenging. But really it comes down to, I think the most important parser is this one, parsing a single crate line. Within each line, what we have to deal with is that there's the potential for empty spaces. And so if we were to just parse each line as a string and then use split or use separate and just sort of get rid of the white space, we're going to miss the fact that this D is in column 2 instead of column 1, and so that would be very bad. So the way we do this with mega parsec is we have two different ways to parse a single crate. Obviously, we have a character within brackets. That's sort of the case where the crate is actually there, but then we also have the case where there's no crate, and that's just the string that has 3 spaces in it. And so in that case, we'll return nothing, indicating that there's no crate in this particular point. Otherwise, we'll return, just a character. And so each line, we have a list of maybe character values. And so eventually, bringing this back up, what we want to do is we want to take a nested list of these and construct our crate stacks. So the nested lists, each of these lists should have the same width. It just might be varying numbers of, nothing or just elements. But ultimately, we are representing our stack of crates with a hash map. So the integer key is just, that's just the number for the column we're at, so that we can reference those using the moves. And then we will treat the stack just as, a list of characters, effectively a string. And we're going to store so that the one that is on top is first in the string. That just, makes sense. And let's see here. So we've gone through all the real portions that actually deal with parsing these characters. It's just a matter of combining these together. So building the crate stack from our, from this parsing section is, a little interesting. We just have to do a couple of folds where we are adding an individual crate with an index into our existing stack. So, okay, brief stack I. This is the this is the previous stack for the index I, and then we can insert into that stack just with this crate. Okay, so little tricky there, a couple of complications with parsing this input. But once we have our crate stacks, then all we really need to do is fold through all of the different moves. So we're using a solve fold down here. Again, all the work really is being done by this function so our fold type, this is just our stack of crates, it's our hash map, and we're taking an individual move and we're saying how does that actually impact our stack of crates. And this part is actually pretty simple. I had an original version where I was actually doing it one at a time, but I just realized it was kind of simpler to do it this way, where we take our initial stack for the source column and our initial stack for the destination column. We get both of these. We'll throw an error if there are no crates. That sort of indicates we've probably messed up somewhere. We'll log an error, we won't throw an error, and just return the previous stack. But otherwise, we are just doing nested inserts into our hash map. So first, we have to modify our source stack. We have to drop the certain number of crates, number given by the move. We have to drop that from our source stack and reinsert this value back in at the source column. And then for the destination column, we have to add these. So we take the number from the source stack, we reverse that because we're sort of putting them back on top of each other, and then we just append that in front of the destination stack. And that's the only update we really have to make with each move. And so now it's just a matter of getting the solution, getting our final string from the crate stack. So solution type, again, I'm using all these aliases, but really we're still just tracking this stack of crates. We want to get a string from that. So let's say we get our sorted results here. We want to take our hash map, turn it into a list. The reason we're sorting is so that we get that first column first and put them all in order, because remember, sorting this list of tuples will that'll sort it by the index of the first one. And then we just drop that and look at each of the individual strings. We use the safe head function so that we can pull the first character out if it exists. Otherwise, we'll get the empty space, which would again probably indicate an error. I wasn't sure what the problem specifications were, but that's all we need, and that's enough to plug this in and give us our solution. So we can actually look at the test cases I have for this. So these are the different tests I had, and they all work if I run. And you'll see I already put my first test case for day 6 in there, so that's why the one's failing, but the day 5 tests all pass. Oh, I forgot to explain the hard part. Part 2 of the problem is not actually hard. Barely anything changes. What happens in part 2 is that instead of grabbing one crate at a time and sort of taking the one on top and then going on top of that, we pull both crates at the same time. So we can pull multiple crates at the same time, which makes this the literal only change in our algorithm from this part is that this reverse actually just goes away. This code is basically identical to this. It just does not. We just don't do the reverse here. And basically all the other logic applies. So that gives us our solution. So that's all for day 5. I'll be back with day 6 again. Hopefully tomorrow. I know I was a little late with this video, so hopefully I will be on time with the day 6 video. But yeah, keep coming back for these solutions. Make sure to subscribe to the Monday Morning Haskell YouTube channel and our mailing list if you have not done so already. And yeah, see you tomorrow.